Welcome back to the stream number 1. Here you will hear our presentation on the simulation use case number 1. I hope this is the presentation you are planning to see. Very warm welcome to this presentation, and I would like to introduce my two co-presenters that are with me today. It is Günther Ehmen from OFFIS. He is a team lead for simulation systems there. And the second co-presenter today is Thomas Platzer. He is working on effectiveness analysis here at BMW. Welcome to the two of you, and thank you for being here with me today. So this presentation is going to be on simulation use case 1, where we built a traffic simulation with the focus on supporting criticality analysis. Now, what that exactly means is something we will see in a bit. But first of all, let's take a look at our agenda. We will start with some introduction of the simulation use case number 1, some motivation. Why do we have simulation use cases in set level at all? What is their focus? And what do we specifically do with our simulation that supports the criticality analysis? Afterwards, we will talk about the theory behind it, which is basically some specification for our simulation, before we take a look at the actual implementation of the simulation. Afterwards, there will be the execution of the simulation and the results we gained from that, before we have a short summary in the end. And of course, we plan to answer your questions afterwards. So I'm looking forward to that. To start with, let's take a look at the big picture for the set level project. Why do we have simulation use cases here in our project? Well, the reason is quite simple. We have a lot of work packages. They all have their different focus and they work largely independently from each other. And we need something that keeps all of that work results together. So in the beginning of the project, we decided to introduce 3 simulation use cases, which will pick up work results from the project and bring all of that together in one simulation. Now, the 3 simulation use cases, we tried to come up with representative topics from real applications, where we can prove that all the results that we actually generate are usable in practice. So we decided to pick one analysis case, which is our use case here, where we conduct a criticality analysis. And then there are 2 more test cases, as Stefan introduced in our morning session today, that deal with a component test and a full integrated system test. Now, all of those use cases or simulation use cases have in common that we want to demonstrate how to use standards, how to also use extensions of the standards that we developed in the set level project. Further, the architecture plays a huge role when it comes to setting up a simulation, when it comes to plugging together different components, different modules, and executing all of that together in one big simulation. This is also something that we want to show with the simulation use cases. Further, of course, KPIs are very relevant for the evaluation of the simulations. And along all of this process, we rely heavily on traceability, which is something we have seen in a previous presentation by Hans-Martin Heinkel. So lastly, one more benefit that we gained from the simulation use cases, and we will also see that throughout the presentation, is that we generate good feedback already during the project on how well the work results can actually be used. But now let's dive into the topic. First of all, I want to take a look at criticality analysis and on the methodological level of such an analysis. Criticality analysis is necessary to reduce complexity, simply said. Well, when we talk about automated driving, we talk about an operational design domain, which is basically the open context. It is an infinite dimensional domain that is very hard to describe. And when we develop automated driving functions, we somehow have to handle this complexity. So criticality analysis mainly deals with how to reduce the complexity and come up with a certain set of abstract artifacts, so to say, that will be a basis for the further development. Now, the way this works, and I'm only going to give a short overview because there is a separate session today afternoon, which is held from our colleagues at the VV Methods project, and they will elaborate a little bit more on this topic. But just a short overview on how criticality analysis works. It starts with some expert knowledge, some data sources, and based on this, there will be criticality phenomena identified. Now, these criticality phenomena are basically influencing factors that will create criticality in a driving scenario. Based on those phenomena, then causal relations will be identified in a subsequent step, which is a combination of one or multiple criticality phenomena, which will lead to actually critical scenarios in traffic. And in order to somehow make all of this manageable, it needs to be abstracted and it needs to be classified so that in the end we end up with some condensed scenario space consisting of a description of scenarios, description of criticality phenomena and how they come together through causal relations. And therefore we have a description for criticality in scenarios. Now, within this whole process, where can we support with simulation? There are two major aspects that I want to point out today. One would be if an expert has already identified criticality phenomena, or also causal relations, this can be tested in simulation. So basically, the hypothesis that this expert has set up will be tested through a simulation and proved or proved wrong, possibly. And therefore, we can use simulation to check whatever has been found through criticality analysis. But a second application for the simulation might also be in the very beginning of this whole process to actually generate scenarios which are critical. And this is the step we took. We started with a scenario and we wanted to find out where there are critical scenarios within this scenario space, which can then be further investigated through criticality analysis. Now, there are two major points that we need in simulation to run a criticality analysis. One of them is the variation of scenarios, just because we don't want to simulate one individual scenario, but we need to simulate scenarios from a whole scenario space. But we will see that later in this presentation. And the second one is we need special metrics in order to be able to measure criticality. Also, this is something that we can expect later in this presentation. For now, I would like to hand over to Thomas to show us what our specific simulation was focusing on.
Thank you, Arun. The simulation goal of our simulation use case 1 is to identify critical scenarios during a right turn on an urban crossing through simulation. Why did we exactly choose this scenario? We chose this scenario because during a right turn, there are different risks which can lead to a critical coincidence or accident. And as weak traffic participants like pedestrians are involved, the potential accident severity can be quite high. There are different aspects which could increase the criticality and therefore must be considered for the assessment of the HUD function. The following topics are high relevant: priority and non-priority, interaction of different agents, especially head function and pedestrian, occlusion, for example, of parked vehicles. Here we see the basic scenario setup, which is composed of a simple crossing with a priority and a non-priority road, as well as predefined routes of the different agents. On the picture, the priority road is the horizontal road and the non-priority road is the vertical road. The white ego vehicle with a head function starts on the right side of the priority road and turns right at the crossing onto the non-priority road. Furthermore, there are more moving agents, for example, 6 surrounding vehicles with predefined routes and 8 pedestrians with also predefined routes. 2 of these pedestrians have to cross the street at a pedestrian crossing on the non-priority road above the priority road. The ego vehicle also must pass this pedestrian crossing after the right turn and then must react to these pedestrians if necessary. For evaluation, we use the time to collision, which is calculated during the simulation, and the post-encroachment time, which is calculated after the simulation in the post-processing. The focus of our simulation use case 1 are the following. So we want to specify and execute the analysis task for assessing criticality. We also want to check the applicability of the architecture and interfaces for our simulation. Furthermore, we want to utilize standards as much as possible, which is very helpful for compatibility of our models. We want to vary input parameters to have many different scenarios for simulation. At least, we want to evaluate criticality by using corresponding metrics. On the following page, we see that for building up the simulation use case 1, we must consider many different components, models, etc. For an easier classification, similar building blocks are equally colored. These building blocks must be combined by best practice for running a simulation of use case 1. Some building blocks are used as framework for the simulation. For example, the simulation platform or the simulation core. In this framework, we must integrate many different simulation models for the ego vehicle, the environment traffic, and the pedestrians. This integration is done by standardized interfaces. Examples for these models are the camera sensor, the HUD function, the motion control, the vehicle dynamics, the driver model, or the pedestrian. For configuration of the simulation, as well as the models, we need some configuration files, especially for the map and the scenario. To reproduce the real scenario as much as realistic, we simulate many different runs, which are built by scenario variation. For evaluating the simulation after all runs, we need results from the simulation, which are written by observer, for example, the TTC observer or the PET observer. Let's have now a look at the scenario variation, and I will hand over back to Arun.
Thank you very much, Thomas. So throughout the next part of the presentation, we will sort all those building blocks and combine them in a structured way in order to execute our simulation. But before we do that, as Thomas said, we would like to take a look at the scenario variation and how that works. So this work is based on results from the Pegasus project. Within Pegasus, there were already 3 levels for scenarios defined, which you can see on the left side of the slide. It starts with a functional scenario. The functional scenario is more or less an abstract description of the scenario that we want to execute. This could be something like, in our case, a right-turning ego agent that drives on a simple crossing, and there are surrounding vehicles and surrounding pedestrians that behave in a certain way. Now, when we want to structure that, we need the next level. We need some logical scenarios, what we call it. This is already a formal description now, where the whole scenario is described, and also parameters are already contained, but might not be fixed to certain values yet, but might be described through distributions. In the example on the right side of the slide, we see that the initial position of the ego vehicle is here described through a normal distribution with a certain mean and standard deviation. Now we also have the possibility to truncate the distribution by setting min and max values, which allows for a control of the scenario in more detail. Now, in order to execute this logical scenario, we will apply some parameter sampling algorithm that will result in concrete scenarios. And here you can already see that from one logical scenario, we generate multiple concrete scenarios, which are then subsequently executed with the simulation system. Now, in the concrete scenario, through the parameter sampling, we end up with having certain values for each of the parameters. In this case, there is a specific value for the initial position of the ego vehicle. Something that is noteworthy here is that it is not only possible to define stochastic distributions, but you could also think about deterministic distributions, which could be something like a vector of values where we want to simulate with each value from this vector one after another. Now, this whole mechanism will be applied to our simulation, as we will see later on in this presentation. One more thing I want to mention here is that this work and the way of describing the logical scenario in a formal way has been done in the Open Scenario Standard through an extension that we developed in the set level project. And this extension of the Open Scenario Standard has already been brought back to the ASAM standardization activity and is actually included in the Open Scenario 1.1 standard already today. But now let's build up the simulation step by step. After we have seen the building blocks and we have seen how stochastic variation works in theory, we want to do it practically now. So when we start setting up the simulation, we have to talk about two different layers for the architecture. The first one is the simulation system architecture. This is basically the whole system that we need to execute one concrete scenario or one concrete simulation. Later on, we will, on top of that, build up a platform architecture that will then allow us to conduct full analysis simulations, which consist of multiple simulations, which include the variation and also the evaluation. But we'll see that later on. For now, let's focus on the simulation system, where we somehow have to couple all the agents that we need in our simulation together with a simulation core. In our case, we decided to go with the open source tool OpenPath, as it already offers great capabilities, and we only had to extend some certain features of it in order to run the simulation. Coupled with OpenPath, we have the three agent types. We have pedestrians in our scenario, we have the ego vehicle, and we have environment, where environment traffic means really the vehicles that are also part of the scenario. First of all, let's start with the pedestrian. This is a rather simple setup here. The pedestrian model is implemented within one functional mockup unit and communicates through OSI messages. So this model is actually an agent model. That means that we don't define trajectories or something like that up front, but we just tell this agent to get to a certain destination. And the whole path will be planned by the model itself. The model will search its way and get to the destination eventually. The model is implemented as a functional mockup unit, which means we can communicate with it through the FMI standard. That made it fairly easy to couple it with the OpenPath simulation core. And for the communication, we use different OSI messages. We need some sensor view in order for the model to perceive the environment. We need some traffic commands so that we can, for example, tell the model where to go in the simulation, tell it the destination. We also have some traffic update that comes back from the pedestrian after each time step and tells us the new position of this model. And then we have one more feature included here, which is an initialization with a ground truth message. That means we send a OSI ground truth message once in the beginning of the simulation so that the pedestrian can learn about the environment, can learn what the static environment looks like, and can perform cost-expensive tasks like map sampling and route planning upfront so that we don't have to do this through the simulation or while the simulation is running. In the same way as we included this pedestrian in the simulation setup, we also include the other models. We always rely on the FMI standard and we heavily depend on the OSI standard, which made it possible to develop the models more or less independently of OpenPath and in the end plug everything together for the actual execution. Now, when we take a look at the environment traffic, we see that the setup is slightly more complicated though. This is because we now don't have only one model, but we couple two models together. The first model is an agent model. It's the driver behavior model, so to say, that controls the environment vehicle. The output of the driver behavior model is then forwarded to the vehicle dynamics, which will execute whatever the driver requests. And from the vehicle dynamics, we get the information back to the OpenPath simulation core, what the new position of this vehicle is after each time step. And as there are multiple environment traffic vehicles, we instantiate this chain multiple times in the simulation. The OSI messages here are pretty similar to what we had with the pedestrian, so I won't go into detail on all of that, but you can see the different messages in the top right, in the bottom right corner on the slide as well. Now, the most complex system in our simulation is probably the ego vehicle. The ego vehicle consists of 4 models that are coupled in a chain. If we start from the left, we have the camera sensor. It's a fairly simple sensor that perceives the environment, but already considers occlusion and some error in the detection. Whatever the sensor detects is then forwarded to the OSI gateway, another functional mockup unit that handles communication with the HUD function. The HUD function is implemented in ROS, so we had to find a way of how to integrate it into our simulation. And we came up with the solution of running the HUD function and running ROS in a Docker container and sending all OSI messages through a TCP channel from our OSI gateway. Whatever the HUD function then returns is forwarded to the motion control. The motion control gets a trajectory as input and will create some dynamics request as input for the subsequent vehicle dynamics model. Within this chain, we will end up again with a new position for the ego vehicle and therefore update this in the simulation core after each time step. We then have 2 more models in the ego vehicle. Those are the observers that Thomas already mentioned earlier. We have to somehow log data from the simulation, and this is done through those models. What they do is basically they perceive the environment through sensor view messages, again, that are standardized OSI messages, and then write corresponding outputs. But we will have a closer look at that in a bit. One more thing I want to mention here with this whole setup is that we use agent models. That means we don't have to pre-compute trajectories, but we rather set up an initial condition. We give all the agent models some destination, and they will act individually in the simulation. And as they can see each other in the simulation, they will also interact with each other somehow, which makes it fairly simple to set up the simulation and also to vary parameters in the simulation, but we get very realistic results from the simulation in the end. Now, I have an overview of all the different models that we used with the corresponding technologies, the input and output messages, which are always OSI messages, and some of the features of the models. I don't think we need to go in detail on this slide, but if you have certain questions, please put them in the comments and we'll try to answer them after the presentation. For now, I would like to take another close look at the observers. So as already mentioned, we log the time to collision and the post-encroachment time, as both of them are expected to be good measurements for criticality in our scenario. With the time to collision observer, we pre-compute the time to collisions live during the simulation, and we only log the calculated values to a TTC log. Within the computation, we assume that based on the current state of the agents will behave and act just as they do in the current state, which means they will continue with the current acceleration and the current yaw acceleration. So we can predict their future path and check what time to collision we have at the certain time step. Now with the post-encroachment time, it's slightly different. Post-encroachment time is not that well known. So said in easy terms, it gives a measure of by how much time two agents miss each other. So it is something that is usually computed afterwards, after the simulation, as you look back at the trajectories the agents took, and wherever the trajectories cross, you will check what simulation has passed between the two agents crossing the certain point. As it is something that is computed after the simulation, the PET observer is fairly simple and just logs all the positions, velocities, and accelerations that we need, so that in the post-processing we can do the actual calculation of the post-encroachment time. And additionally to this TTC and PET log that we get, we also have some log outputs from the simulation core OpenPath, which is in general all kinds of logs that are written, but also the output and the cyclics of the whole simulation. How this is used, we'll see later on. For now, I want to talk a little bit about the configuration of the simulation, which is basically the last step that we need before we can run a simulation. Here we have the Open Drive standard, also one of the ASM standards that we used for defining the map. Within the map, we have definition of the road infrastructure. All the road markings are defined here and the traffic signs. This is more or less the static scene that we are operating in. Additionally to the Open Drive, we use an open scenario file that gives us agent definitions, that states where all the agents are placed in the beginning of the simulation, what their initial velocities are, but also what destination they should reach eventually in the simulation. And as the third pillar for our simulation configuration, we have certain OpenPath specific configurations, which, for example, define the logging, but also the SSP standard that we used here in order to define the combination of several simulation models within those chains as we need them for the ego vehicle and the environment traffic. With all of this set up now, we have a good structure in our building blocks from the beginning, and we're actually able to execute a simulation. Let's take a look at that. Here we can see that in the beginning we have some initial condition as it is described in this scenario, and then the vehicles will start driving, the pedestrians will start walking, and they all have their destination in mind and are trying to reach it. From the right side, we see the white vehicle coming in that is now turning. This is the ego vehicle with the HUD function. And you saw that there was a pedestrian crossing. There is a second pedestrian now crossing. And we can see that there is a lot of interaction actually happening in this scenario. Now in this view, it's a little more obvious how the pedestrians behave. You will see now from the left side, the ego vehicle is coming into the crossing. And we also have a parking car here, which is occluding some of the view for the ego vehicle, which makes it more interesting if the ego vehicle will see the pedestrian in time or not. Also, we see the second pedestrian crossing here, and the ego vehicle manages to brake and lets the pedestrian cross. As you saw, now we're able to simulate the scenario, but it will get more interesting when Günther now shows us how we introduce variation in this scenario. Günther, the stage is yours.
Thank you, Arun. Now that we can perform simulation runs using the simulation models, we have to deal next with the specific execution of many simulation runs, as well as the variation of the scenarios and the evaluation of the different simulation runs. For this purpose, we have extended the just shown simulation system by various components to a kind of simulation platform with a focus on modularity, flexibility, and automated execution. As input, the simulation platform receives an analysis task with specific information for the simulation task, as well as the platform configuration. The analysis task, for example, consists of the KPIs for the evaluation, the data format for the evaluation report, the path to the logical scenario, the distribution types for the parameter variation, and the number of scenarios to be generated. The platform configuration consists, for example, of specific parameters for the simulation core, the used simulation models, the coupling of these simulation models, the evaluation components, and the type of concrete scenario generator to be used. Currently, both of these files are implemented as well-structured and human-readable TOML files and are imported by the platform runtime control, which is part of the simulation platform management, which handles the operation of the individual components of the simulation platform and is depicted in the middle of the figure. At the beginning, all information necessary for scenario generation is forwarded to the scenario manager, which handles this process. The scenario manager organizes the scenario handling and generates a defined number of concrete scenarios with the help of the concrete scenario generator. The scenario generator receives therefore as input the logical scenario with the parameters to be varied, as well as the variation technique to be applied. After the successful generation of the concrete scenarios, the platform runtime control then triggers for each generated scenario a simulation run. The platform runtime control hands therefore over a scenario and the simulation configuration to the simulation system, OpenPath in our simulation, and then starts the execution via a dedicated runtime command. After each simulation run, the output data then is stored in the external data storage, with this depicted in the lower part of the figure. Arun, could you please? Yeah, there is it. At this stage of the development, we use the local file system for storing the simulation results, and the used file formats here are comma-separated value and XML. In the future, the data storage can be realized, for example, by a database in order to be able to perform different analyses on the simulation data and to allow a distributed access. The data storage is also used for storing the evaluation results and provides the database for visualizing the simulation runs, as just shown before in the video by Arun. Finally, the simulation results are evaluated in the evaluation system. After execution of all concrete scenarios, the evaluation manager receives the evaluation criteria from the platform runtime control and triggers the individual evaluation modules. Here we use the time to collision and the post-encroachment time, two modules, as criticality metrics, and the results then of the individual evaluation modules are made available to a report generator, which then generates a markdown document or a comma-separated value file as an evaluation report. We will see some screenshots from the evaluation report later on. The platform management and the evaluation system, as shown here in the figure, are implemented in Python and thus enable an easy extension or adaptation of the platform. The whole workflow, from the sampling of concrete scenarios to the generation of the evaluation report, is fully automated. Okay, so next, let's take a look to another video. In this video, we give an insight into the parameter variation and the evaluation of the simulation runs. We thereby vary the initial position and the target speed of the ego vehicle and of the two pedestrians. Furthermore, we have a parked vehicle in the front area of the intersection that provides a potential occlusion of the pedestrians. As said before, we use the time to collision and the post-encroachment time between the ego and the pedestrian as criticality metrics. The time to collision is calculated online and the post-encroachment time offline afterwards. We then implemented a stochastic variation of the scenario parameters and generated 10,000 concrete scenarios from a logical one, as shown in the slide before. Each scenario is simulated and the results were stored in the data storage and evaluated afterwards. Here we have a detailed look into a simulation run with the focus on the TTC and the post-encroachment time. The ego reaches the intersection and the time to collision observer calculates a time to collision of 7.9 seconds based on the predicted movement. When the ego enters the intersection, a time to collision of 3.2 seconds is calculated. The post-encroachment time between the ego and pedestrian in the crosswalk is about 4.4 seconds. Shortly after leaving the intersection, a time to collision is collected between the ego and the second crossing pedestrian. The pedestrian stops walking and the ego vehicle can pass. Finally, the pedestrian crosses the road, and this leads to a post-encroachment time of approximately 2 seconds in this scenario. An evaluation of this type was performed automatically for all 10,000 simulation runs by the evaluation system. On the next slide, we will see the results of the time to collision evaluation over all simulation runs, separated according to both pedestrians, where pedestrian 1 is the pedestrian crossing the road in the intersection as shown in the video. As we see, in the majority of the simulation runs with pedestrian 1, the time to collision was above 20 seconds, and thus is a no critical traffic situation. Nevertheless, a cluster of time to collision between 0 and approximately 5 seconds with 2 peaks at 0 and 1.5 seconds is recognizable. Furthermore, it can be seen that there are more runs with a lower time to collision when the pedestrians are possibly occluded by the parking vehicle. In the figure on the right side, there are also a lot of simulation runs with a time to collision above 20 seconds. But much more simulation runs have a time to collision of exactly 1 second. These are by far no critical traffic situation, but a result of the behavior of the pedestrian agent after it has reached its target position. After reaching the pedestrian, agent turns in a circle on the spot, and this is misinterpreted by the time to collision observer when the ego passes the pedestrian. Without considering this peak, 2 clusters are recognizable. One cluster reflects the traffic situation where the ego is in the intersection area and the second pedestrian is already crossing the street. The other cluster rather reflects the situation just shown in the video, where the pedestrian tries to cross the street when the ego has already covered a part of the way. On the next slide, the variation of the post-encroachment time between the ego and the 2 pedestrians is depicted. Again, the 2 peaks at about 20 seconds, which means no post-encroachment time could be calculated, are the result of a very defensive driving style of the driving function, which leads to deadlocks in various traffic situations in which the ego vehicle stops due to a nearby pedestrian or a nearby other vehicle and does not start driving again. So there is no post-encroachment time calculable. A post-encroachment time of 0 is also sometimes related to deadlocks. In this case, both agents have entered the conflicting area and never left them. Beside these deadlock situations, there is again an effect of the occlusion visible in the results. In relation, the post-encroachment time between the ego vehicle and pedestrian 2 is larger in the simulation run with occlusion than in the simulation run without occlusion. This is probably due to the fact that in the simulation run with occlusion, the vehicle often remains longer in the intersection area, and thus the second pedestrian has already crossed the road at an earlier stage. In summary, it can be seen that the generation of scenarios, including the parameter variation with a subsequent simulation and exemplary evaluation, could be successfully carried out and can thus serve as a basis for further work within the field of the criticality analysis. But what about the performance? On this slide, we have a few facts about the performance of the execution of the simulation platform. We performed a different number of simulation runs on 4 different machines and distinguished between the simulation execution, depicted on the left side, and the simulation evaluation, depicted on the right side. The execution environment is a Linux in each case, whereby the Windows subsystem Linux in version 2 is used twice. Each simulation scenario has a duration of 40 seconds, as already shown in the video. First of all, the duration for the generation of the concrete scenarios is negligibly small and thus not taken into account here. In the current implementation, the simulation runs are executed sequentially, followed by the evaluation. As we can see, the simulation time increases almost in a linear way with the number of simulation runs. The situation is very similar with the execution time of the evaluation modules. The impact of the processor generation with regard to the multi-threading capability is mainly noticeable in the evaluation. In the pure simulation, on the other hand, the read-write access to the storage medium and the execution time of the simulation models are more relevant. The toolchain runs also stable over a large number of simulation runs, also in conjunction with the Docker container of the automated driving function. In the current implementation, one identified bottleneck is the write access to the storage for the log files and the debug stuff. Therefore, we will optimize the data output in future, and we will analyze the possibility to connect the database for data management to reduce the read-write accesses. Furthermore, we will parallelize the simulation execution and the evaluation. An initial idea here is to use Docker containers for the simulation system, similar to the driving function, to allow multiple instantiations. At this point, I will hand over again to Arun.
Thank you very much, Günther, for those insights on our simulation platform, on the evaluation of the simulation. Now, before we come to the conclusion, I want to summarize again what standards we actually applied and what extensions we made to them, as this is one major part of the satellite project. Now, all of the simulation models have been developed by individual partners, and we had to bring all of that together in one simulation. This would not have been possible if we would not have been deciding and relying on all those standards that we used to couple the simulation models and to parameterize the simulation. So what we actually used is, as we have seen throughout the presentation, the Open Scenario 1.0 standard for description of the scenario. And we did not only use it for the concrete scenario, but we also used it for logical scenarios, where we are able to describe parameters through stochastic and deterministic distributions. As I already have said, this has already been transferred to the ASAM and is part of Open Scenario 1.1. For the description of the map, we use the OpenDrive 1.6 standard, and within the simulation models, we use the FMI standard to wrap all of them as functional mock-up units. Communication has happened through OSI 3.2.0, so the Open Simulation Standard. Here also we have made a lot of extensions by creating new messages or extending existing messages, and all of that is also something that already is or will go back to the ASAM standardization activities. Also with the OSI messages, we introduced a new way of using a ground truth message to initialize models upfront to the simulation to save performance during the simulation execution. And lastly, we used SSP, the System Structure and Parameterization Standard, in order to couple multiple FMUs to a chain of FMUs that will represent one or several agents within our simulation. Now, aside from those standards, we have today seen how to set up the simulation for an analysis task. In our case, it was the simulation that is needed to identify critical simulations that can then be used during a criticality analysis. We developed simulation models, we developed platform tooling, and we developed the simulation core that enables us to conduct the simulation, to set it up through a predefined architecture, and couple all the models with the standards that I just mentioned. Now, in the end, we were able to execute the simulation fully automated. We ran 10,000 test cases to show that it works. And within the evaluation, we were able to see great differences through the variation mechanism. Now, what are we going to continue in the second half of the project? We are planning to further focus on standards and the technologies to extend them and use them in an even bigger simulation. We also want to improve the agent behavior, as we saw that there are still some side effects, which we will address in the upcoming part of the project. Further, we will increase the complexity in the map and the scenario, and we will also take a closer look at the evaluation metrics for criticality. Now, for now, I would like to thank you very much for watching our stream. And we have some time left for questions. And I'm very curious, Thomas, do we have any questions?
Yes, thank you, Arun. We have really many questions. And I will just answer the first one. It's a question for Günther. How do you instantiate vary parameters? Only by sampling from some predefined probability distributions?
We use here a script which was developed by DSpace in our simulation setup. And it's possible to define different variation techniques and variation areas for the parameters. And then the parameters will be varied using these mechanisms. And therefore, you have to change the logical scenario with the parameter ranges in the from the concrete scenario.
Okay, thank you. One other question is for the behavior of the pedestrians. How do you handle different behavior of other traffic participants, cautious or risky, even timed to aggressive behavior, especially the interaction with the ego vehicle is in a reactive or even proactive cooperative manner? I think it's a question for you, Arun.
Yeah, thank you, Thomas. This is a very interesting question, actually. For now, I mean, those simulation models are obviously parameterizable. So we could imagine setting parameters for the specific behavior if they are more careful or more aggressive. So this is one way. Actually, for this simulation, our focus was on integrating the agent models and especially the pedestrians in a way that they work well together in the simulation. So right now we have not done such a variation, but this is exactly the direction we want to go into in the second part of the project. Additionally, one thing I want to mention here is we could imagine that a pedestrian always stops on the side of the street as it already can see the ego vehicle coming in our scenario. Now, a mechanism that we have come up to tackle this issue is that we can tell the pedestrian through some sort of traffic command to ignore certain other agents. Basically, we're telling the pedestrian not to see the ego vehicle in this case, and therefore we can force the pedestrian to cross the street regardless if a vehicle is coming or not. So there are certain ways on how to influence or manipulate agent behavior, and this is also something that we're planning to show in the upcoming months of the project. But also today afternoon, there will be a presentation on agent models in general. And I think there will be also a demonstration on pretty much this topic. So if you're interested in it, check the simulation or the presentation out.
Okay, thank you. Also, one further question regarding the pedestrians is in OSI right now, only the positions of the pedestrians can be sent. How can this be integrated with other sensors in future? For example, camera sensor to analyze gestures.
This is another great field of work, I think. Right now, as you said, it is possible to set the position of certain agents, for example, pedestrians. It is also possible to define that this type of agent is actually a pedestrian. So there is some knowledge about that. But actually, OSI is still lacking detailed messages for certain applications, like defining the state of a pedestrian or the actual movement and position of arms and legs and things like that, which will be relevant especially when it comes to detailed sensor models that can detect pedestrians based on their current position or movement. But this is definitely a topic for further work.
Okay, thank you. I think there are some further questions possible. Sometimes the question was which driver model is used. That means how are decisions of the drivers made?
So the driver model here is a simulation model that has been implemented within the set-level project by the IKA in Aachen. This model is partly already open source available, but also will become completely open source available during the project or at the latest at the end of the project. But therefore, it is a project that is specific, or a model that is specifically developed within the set-level project for the application that we just saw, and some further simulations that are already executed within our project.
Okay, thank you. And one last question is, where is the scenario engine running? Is it part of the simulation core?
The short answer would be yes. Currently, it is part of the simulation core. The scenario engine for the Open Scenario 1.0 standard is currently tightly coupled with OpenPass. This is just due to the fact that with OpenPass, we already started using the Open Scenario standard very early, and we kept on implementing more and more features. However, we saw it in the presentation from Jochen earlier today that there are activities of decoupling the scenario engine from the simulation core. And this is something we are also doing with OpenPass currently, so that there can be results expected within, I would say, later this year. There are activities going into that direction of taking the scenario engine apart from the simulation core and coupling it through some sort of interface.
Okay, thank you. And I think one last question is possible. It's a very detailed question. Why does the HUD function only use the info from the camera sensor?
This is a good question too. Well, obviously, a lot of different setups are possible here, and I mean, the person who asked this question was probably not able to attend the simulation use case 1 in parallel, simulation use case 2 in parallel. But they used the same HUD function with a different setup. And it basically just depends on the simulation you want to execute and how you want to set up the agents for this specific simulation. In our case, the focus was on detecting critical simulations, or critical scenarios, actually. Therefore, we decided not to overcomplicate the setup of the ego vehicle, but just use the HUD function with its easiest setup, which was, in our case, one camera sensor. The HUD function itself would be capable of using more sensors. It is something that has been done in simulation use case 2, but for detecting the critical scenarios, we decided to only take the camera, also as it somehow limits the detections from the ego vehicle, and we will probably get more critical scenarios by using less sensors. So this is the reason why we decided to use this specific setup, although technically it would have been doable to also integrate more sensors.
Okay, thank you very much, Arun. I think we are out of time, so we will finish the question and answer session.
Thank you very much, Thomas, and thank you to the audience for all those questions. I can see that there is high interest in this topic. Thank you very much for all those questions. And just for you to know, we will now have a lunch break till 1 p.m. And at 1 p.m., we will directly begin in the separate streams. So make sure you dial into the stream that you are going to follow today afternoon. And also, I'm looking forward to answer more questions and have interesting discussions today afternoon in the virtual coffee. See you later.